All right, welcome back to another episode. We are covering metabolic acidosis today. Um, so let's just get right into it. Number one, metabolic acidosis, by definition, again, it's a decrease in bicarb, right? So let's just start drawing out the steps of how to navigate these problems and kind of my approach and my method. So, number one, um, pH. Number two, bicarb. Simple enough. So once we've identified a decrease in our bicarb and a decrease in our pH, the question becomes, or we've identified that we're in metabolic acidosis. Now the question is, what type of metabolic acidosis? And there's two types. Okay. Number one is there's an anion gap, and number two is there's no anion gap. We've already explained the concept of electroneutrality. Um, and what the anion gap actually represents. Normal gap. All right. So in order to identify if there's an anion gap or not, of course you have to apply our lovely anion gap formula where we can see at the top of our algorithm there. Okay. Another point I should make is that when you're calculating the anion gap, make sure you correct for albumin using the calculated anion gap plus 2.5 times 4.4 minus the albumin. Because again, albumin is a negatively charged protein and sometimes can artificially decrease the anion gap if it is in fact reduced. All right. So after we identify whether or not we're in a normal anion gap or an increase in anion gap, of course, if we have a normal gap, this is going to be called always hyperchloremic. Hyperchloremic normal gap metabolic acidosis. I'm going to save time and not write that out. Whereas the anion gap will have a normal chloride. All right, so now the question becomes, what can cause a normal gap versus an anion gap? Really quick to round out our hyperchloremic normal gap metabolic acidosis. Number one, by and large, is diarrhea. Number two can be saline, so a ton of saline. Obviously, saline has chloride in it, and it can lead to a very large increase in chloride. And of course, to maintain electroneutrality, the body's going to decrease the amount of bicarb reabsorption, or it's going to excrete bicarb to maintain electroneutrality. And then there's more rare causes such as renal tubular acidosis, etc. If we have an anion gap and a normal chloride, then the question becomes what's causing this? And I think I'll cover the delta now and the concept of the beautiful delta. So you have to understand that by definition, metabolic acidosis, decrease bicarb. Well, the amount of increase in acid, or the amount of divergence is a better way to put it. The amount of divergence away from the normal anion gap should equal the change in bicarb concentration. That's really all the gap metabolic acidosis is saying, is that, and it makes perfect sense. We have to go back up to our electroneutrality. If we look at this high anion gap state, It's saying that however much this increases, right? So however much this increases, this should decrease the exact same amount. I mean, it's pretty simple, folks. And so the purpose of the delta delta is to identify if there's another um, metabolic disorder. So this tells us an additional metabolic disorder at play. Because if the amount that changes from the anion gap, let's just say, is 10, so let's just say we calculated a gap of 22. That means a change from the anion gap of 10, which means that there should be a decrease in bicarb of 10, right? So again, you're increasing the anion gap and then you're decreasing bicarb simultaneously. So that's the principle behind the delta delta. So when we're navigating this algorithm, the first thing we want to do is look at the pH, look at the bicarb, and then ask ourselves: is this a a normal gap metabolic acidosis or an increase in anion gap metabolic acidosis? We've already covered some of the conditions seen in the normal gap or hyperchloremic metabolic acidosis, and we discussed when you would use the delta delta formula and kind of the conception behind it. You only use it when you have an increase in anion gap, and of course this comes with a normal chloride, and the amount of change you are from the normal gap should equal the amount of decrease or the amount of change you have from the normal level of bicarb. So lastly, if we have an example, then let's say that the gap is 32, and then what should the change in bicarb be? Well, the amount of change from the normal anion gap, normal being 12, would be 20. So the change of Ag equals 20. Then that means that the amount of change in bicarb should also be 20, right? Makes perfect sense. So what would this be then? This would be, if normal is 24, this would have to be 4. And then if the value is not 4, you know that there is something else going on at play. If the value is less than 4, that would mean we have an even further reduction in bicarb from expected. So that would mean that we would have an additional metabolic acidosis going on. And vice versa. If we have an increase or a value that's above 4 in our bicarb, we know that something else is increasing the bicarb, so likely it's going to be a concomitant metabolic alkalosis at play.